Neutron stars, some of the most bizarre and fascinating objects in the universe. Imagine a star, once massive and burning bright, that has collapsed under its own gravity after exhausting its nuclear fuel. What's left behind is an incredibly dense core, made almost entirely of neutrons, packed together so tightly that a sugar cube-sized amount of this material would weigh as much as a mountain on Earth. These stellar remnants, known as neutron stars, are the densest objects in the universe, second only to black holes. But their story becomes even more captivating when two neutron stars come together in a cataclysmic event known as a neutron star merger. Neutron star mergers are not just simple collisions. They are among the most extreme events in the cosmos. When two neutron stars spiral towards each other and finally collide, they create a burst of gravitational waves, ripples in the fabric of space-time, that can be detected by observatories like LIGO and Virgo. These gravitational waves provide us with a direct way to observe the violent dance of these dense objects, giving us insights into the most fundamental forces of nature. But the collision itself also releases an immense amount of energy, manifesting as a kilonova, a powerful explosion thousands of times brighter than a classical nova, lighting up the surrounding space. Yet the most intriguing aspect of these mergers might be what happens in the aftermath. In the milliseconds following the collision, the resulting object, whether it becomes a hypermassive neutron star or collapses into a black hole, experiences conditions so extreme that they could lead to the formation of quark matter. Quark matter is a hypothetical state of matter where quarks, the building blocks of protons and neutrons, are liberated from their usual confines within these particles and move freely in a sort of quark-gluon plasma. Normally, quarks are never found in isolation. They are bound together by the strong force, mediated by particles called gluons, within protons and neutrons. This force is so powerful that quarks are almost impossible to separate under normal conditions. But the aftermath of a neutron star merger is anything but normal. The immense pressure and temperature might be enough to overcome the strong force, freeing quarks from their bonds and allowing them to exist in a free state, something that hasn't been seen since the universe was just a few microseconds old, right after the Big Bang. So why does this matter? Understanding whether quark matter is created in neutron star mergers would be a groundbreaking discovery, shedding light on one of the most fundamental aspects of particle physics. It would provide a unique opportunity to study the strong force under conditions that are impossible to recreate in any laboratory on Earth. This could help answer deep questions about the nature of matter itself and the early universe. Inside neutron stars, the pressure is so high that atoms are crushed into neutrons, and in the core, these neutrons might themselves break down into a soup of quarks. The existence of quark matter within neutron stars has been theorized, but direct evidence is elusive. The idea is that in the core of a neutron star, the density is so great that protons and neutrons dissolve into their constituent quarks, forming a dense, exotic form of matter that is radically different from anything we encounter on Earth. During a neutron star merger, the combined mass and gravity create a scenario where densities and temperatures could skyrocket even further, potentially triggering the transition to quark matter. If quark matter forms, it would be a temporary state, lasting only milliseconds before the merged star either stabilizes or collapses into a black hole. But even in this brief moment, the creation of quark matter could have significant implications for our understanding of physics. One of the key aspects researchers are investigating is the viscosity of this quark-gluon plasma, the stickiness of the quark soup. Viscosity, in this context, refers to how easily the plasma flows. If the quark matter has high viscosity, it means that the quarks and gluons interact strongly with each other, resisting flow. A low viscosity, on the other hand, would suggest that the plasma flows more freely, with weaker interactions between particles. This concept is closely related to bulk viscosity, which describes how the material's density changes under oscillations. During a neutron star merger, the newly formed quark matter would experience rapid compression and expansion due to the intense gravitational forces at play. These oscillations could cause the quark matter to lose energy, a process that would be governed by its bulk viscosity. To understand these properties, researchers are using theoretical approaches like holography, a concept derived from string theory. Holography suggests that the behavior of certain strongly interacting quantum systems can be described by a simpler theory in a lower dimensional space. This method allows physicists to model the behavior of quark matter under the extreme conditions of a neutron-star merger, providing insights that would be otherwise impossible to obtain. Another approach is perturbation theory, a method used in quantum field theory to approximate the behavior of particles when interactions are relatively weak. By combining these two methods, researchers can estimate the bulk viscosity of quark matter and predict how it would behave during a neutron-star merger. The results from these studies indicate that quark matter might indeed form during these collisions, and that its viscosity could be lower than previously expected. But what does this mean for our understanding of the universe? If quark matter is produced during neutron-star mergers, it could leave a unique signature on the gravitational waves emitted during the collision. These signatures might manifest as subtle changes in the gravitational wave signal, providing a new way to probe the conditions inside these extreme objects. Detecting such effects could confirm the existence of quark matter and offer a glimpse into the behavior of matter under the most extreme conditions. Moreover, studying these collisions could also offer insights into the early universe. Just moments after the Big Bang, the universe was filled with a hot, dense quark-gluon plasma, similar to what might be produced in neutron-star mergers. By understanding how quark matter behaves in these events, we can learn more about the conditions that existed in the first moments of the universe and how the fundamental forces shape the cosmos as we know it. The implications don't stop there. Neutron-star mergers are also key to understanding the origins of some of the heaviest elements in the universe, such as gold and platinum. These elements are thought to be forged in the violent environment of a neutron-star merger, where the extreme conditions allow rapid nuclear reactions to occur. By studying these mergers, scientists can gain insights into the processes that create these elements and distribute them throughout the universe. In recent years, our ability to detect and study neutron-star mergers has improved dramatically, thanks to advances in gravitational wave astronomy. The first detection of a neutron-star merger in 2017, known as GW17817, marked a new era in astrophysics. It was the first time we observed both gravitational waves and electromagnetic radiation, light, from the same cosmic event. This multi-messenger approach provides a more complete picture of these collisions, allowing scientists to study the aftermath in unprecedented detail. As we continue to observe more neutron-star mergers with increasingly sensitive instruments, we're likely to uncover new and unexpected phenomena. Each new detection brings us closer to answering fundamental questions about the nature of matter, the forces that govern the universe, and the processes that drive some of the most energetic events in the cosmos. However, there are still many mysteries to unravel. For example, what happens to the merged object after the collision? Does it become a stable neutron star, or does it collapse into a black hole? And if it does become a black hole, what role might quark matter play in that process? These are questions that scientists are eager to answer as they continue to study these extraordinary events. In conclusion, neutron-star mergers are not just spectacular cosmic events. They are laboratories for studying the most extreme physics in the universe. The possibility that these collisions might produce quark matter, a state of matter that hasn't existed since the early universe, opens up new avenues of research in both astrophysics and particle physics. As researchers continue to explore these events, we may soon unlock new secrets about the fundamental nature of the universe itself. So, the next time you hear about a neutron-star merger, remember that what's happening out there is more than just a cosmic collision. It's a window into the deepest, most fundamental workings of nature, a glimpse into the origins of the universe, and perhaps the birth of something entirely new.